Hey, my fellow letter lovers. This is NoNumberMan, and today we are going to look at buffers and VAOs in OpenGL here in C#. So, of course, if you've not seen the previous episodes of this Let's Create a Game in C# series, we are using OpenTK for all of our OpenGL bindings. And we have already created a little bit of a framework for our game to run. So let's just show it right here. Here we go, hello world, and we get a nice green triangle. Right, so as you can see, we've already created a very small buffer/VAO setup. But I want to just get rid of all this. So let's select all of it, get rid of it. And then I want to start over again. And I want to go over every little step that is involved with creating buffers in OpenGL and with creating VAOs and how to use those to actually show something on screen, right? Because if I run it now, there is nothing on screen. Of course, it's just the background, which is red, but the triangle is gone. So let's get right into it. So the first thing that we are going to want to do, of course, is create a VAO. So a VAO essentially is just an OpenGL object that can store buffers. And buffers are just OpenGL objects that can store data. So I want to gen vertex array and I want to gen buffer. Now, the next thing that we are going to want to do is, of course, bind them. So now we've just created them, but OpenGL isn't using them yet. If we now bind them, so bind vertex array, then we will tell OpenGL to actually start using this. That is very important for the next steps, of course. Then we can also bind the buffer. Now, here's something interesting is going to happen. We are going to have to specify a target, a buffer target. Now, there are a lot of these. As you can see, we have array buffer, atomic counter buffer, copy read buffer, copy write buffer, so on and so forth. There are a lot of them. Now, for us, we are going to want to use an array buffer. And that is because array buffers are specifically intended for storing vertex data for rendering, right? The other buffers are used for various other purposes, and we will get into those in a later video on advanced buffers and VAOs, because we do not have time to cover all of these in one video. There are just too many of them. So we'll just focus on the array buffer for now. All right, and then next, of course, we want to have the actual ID of our buffer in here. So now that we have told OpenGL that we want to use this VAO and that we want to use this buffer specifically as an array buffer as well, we can start actually putting data in there. And because the buffer is the thing that actually stores the data and the VAO just stores buffers, we'll first have to populate the buffer. All right, so what we're going to have to do is buffer data. gl.bufferData, there we go. So buffer data is intended to be used for mutable buffers, which means that you should be able to change the data inside of your buffers at a later point using this function. Now, if you already know that you do not want to change your data later, then you can also use BufferStorage. And this will create a buffer that cannot be changed later, or which contents cannot be changed later. All right, but for now, we will use the more versatile one. So we will use buffer data. Of course, if you can change the buffer data later, you do not have to. So buffer data is just more versatile in that regard. The first argument that we are going to have to specify is the buffer target. And that is just the same as the buffer target that we have specified here earlier. So what we are saying here is in this line, let me zoom in a little bit. In a GL bind buffer, what we have here is we are binding our vertices buffer to, let's just say, an array buffer register, right? Something like that. So now in the buffer data, we are going to have to specifically write to the buffer that is bound to the array buffer register, quote unquote. So that is why this absolutely has to be the same. If it's not the same, you are not writing to the buffer that you want to. Okay, next up is the size. So the size is just, oh, well, it actually says it in the description here. Specifies the size in bytes of the buffer object's new data store. So basically what it means is just the size of the array that you want to put in your buffer in bytes. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 entries in our verts array. All of these are floats, so that is 4 bytes per value. 9 times 4 is 36. Of course, in C# and also in C++, you can also do something like verts.length or verts.size, and then multiply that by the size of whatever is inside of your array, so float. And that should also give us the right value here. Right, next up is the actual data. Now, there are many ways in OpenTK that we can reference our data. One of those is to just pass an array like this. That is completely fine. That is usually the easiest way to do it. Of course, you can use int pointers. You could also use normal pointers. In C++, of course, you would have to use regular pointers, right? In C#, regular pointers are considered unsafe code. So it's usually better to avoid those whenever you can. Of course, behind the scenes, OpenTK will convert this array to an unsafe pointer and then use that to call the native OpenGL code. Now, the next value here is buffer usage hint. Now, there are also quite a couple of these. And you'll see that they are basically just combinations of the same couple of words. Static draw, you have dynamic draw, and you have stream draw. We have dynamic copy, dynamic draw, and dynamic read, and so on and so forth. So there are two sets of words here. We have the draw, copy, and read. Now, draw means that we just want to use this buffer to write to. We do not want to read from it. And something to keep in mind here is that we specifically do not want to read from it. The GPU and your shader code can read from it, but here on the CPU side of things, here in our Visual Studio, we cannot use this buffer to read from it. But using the draw, we can change the data and write to that buffer still. Now, if we use the read value here, that means that we cannot write to this buffer again. Of course, we can write to it here. Well, we'll have to, right? We'll have to set the data at least once, but afterwards we will not be able to change the data inside from the CPU side of things. Take that with a grain of salt because these are just usage hints. So if you do write to this buffer afterwards, nothing weird is going to happen. You're not going to crash because again, these are just hints. So they are not strict rules. But the driver might try to optimize this OpenGL code for the usage hint that you have specified here. So it's probably a good idea to actually specify what you want to use it for and actually use it for that and not break these hint quote unquote rules, even though you can, of course. Now the last one is the copy one, and that means that you cannot write or read to this data anymore. Now next are these first words. You have static, stream, and dynamic. Static means that you intend to just write to this data once, and then maybe once or twice over the long run, but really not more than that. If you use the dynamic word here, the dynamic hint, then you're basically saying, well, I want to write to this data from time to time. I want to do it, well, maybe like every 5 frames, maybe every 10 frames. I just want to write a bit of data to it. So it's more than static, but it's less than stream. When you specify stream, then you mean that you want to constantly keep updating the data inside of this buffer. So after every frame, maybe every other frame, you want to update that data. And again, these aren't hard rules, these are just hints, but the driver might try to optimize your code for whatever you have specified here. So it's probably a good idea that you kind of stick to what you write down here. For what we intend to do, we just want to write to it once. So that would be a copy, probably, right? We don't want to read it. We don't want to write to it anymore. Just a copy. And yeah, so a static copy, basically. Now, in many tutorials, you will see static draw here, and that would allow you to update the data from time to time if you want to. And that is totally valid. That is totally valid. But for now, we are not going to update the data inside of our buffers dynamically after we've already assigned it. Now, we will try to do something like that in a later video on advanced buffers and VAOs. I think that would be very instructive, but again, we don't have time for every single thing in one video here, unfortunately. I do think that updating buffers dynamically is a more advanced feature of OpenGL. Next up, it is important to enable the VertexAttribArray. And we have two versions here. We have EnableVertexAttribArray and we have EnableVertexAttribArray. You want to get the EnableVertexAttribArray. You can also see that the top one requires version 4.5, which is quite a late version of OpenGL, quite a new version. And EnableVertexAttribArray just requires 2.0. That is the one that we want to get. And what EnableVertexAttribArray allows us to do is it allows us to enable this index input in our shaders. So let's quickly hop into our shaders. So here we have it. I'm going to open this with Notepad. And then here we go. So last time when we worked on the shaders, we have specifically set here location equals 0 on our vertex position input variable. And this location equals 0 is very important. That is the index of this input data. And that is why we have to enable that index here. So this 0 and this 0 have to be the same. I could, of course, specify a 1 here, save it, specify a 1 here. But of course, it makes sense from a programmer perspective to start off with 0. All right, then the next thing that we want to do is we actually now want to put the buffer inside of the VAO. So how we're going to do that is like this. We can do GL dot vertex attribute. Then I do, of course, have to write it correctly. Pointer. Vertex attrib pointer. There we go. So this is basically just going to put that buffer data into the VAO, and it is going to give some context to that buffer data such that the VAO can use it effectively. So first off, the index, that is again the same index of your shader input data. So that's again going to be 0. Here it just enables that index for the input data. Here it will actually put the data into that index. Right, then the size is just the number, here it actually says it, the number of components per vertex attribute. So basically we're saying here that every vertex is going to require 3 entries of our buffer or of our array, right? The X, Y, and Z, X, Y, Z, X, Y, Z. Every time it is 3 entries of our buffer / our array. Then we have the vertex attribute pointer type, and that just specifies the type of data that we want to put in there. So of course we have floats, bytes, doubles, we have integers, shorts, all of those, right? We have floats in here. So as you can see here, we have a float array, so this should be a float. Next up is normalized. Now, normalize is kind of interesting because for floats, this doesn't matter at all. This does literally nothing. But if you have a fixed point data type like a byte, then if you set normalize to true, it will actually normalize that fixed point data to a floating point number. So let's say you have an array with 255 as your byte data in there. Then this normalization step will change that to 1.0 in a floating point value. And of course, half of that, 127, will be converted to about 0.5. And 0 will be converted to 0.0f, right? But again, if we are already putting floating points in here, this does literally nothing. So we don't necessarily have to worry about that here. Next up is the stride, and the stride basically tells you how much data is in between each vertex entry. So let's say we have a vertex point like 1, 1, 1, and then next we just have some garbage. Let's just put some garbage here. And then again, we have our second vertex data 2, 2, 2. And then again, some garbage. Now that means that between every valid vertex point are 3 values of garbage. And then 3 values that we actually want, and then 3 values of garbage again. That means that we should put the value 3 in here. And that will mean that after every vertex that it reads, it will skip the next 3 values and then read the next vertex, skip the next 3 values, read the next vertex. Right? Wrong, actually. This is editing me. Hi. And yes, so I made a little mistake there. Stride does not necessarily specify the distance between one bit of vertex data and the next one. It specifies the full distance to the next vertex data point. So including that first bit of data. So actually, for a data set that looks like this, the stride would actually be 6 and not 3, because we need to go 1, 2, 3, 4, 5, 6 before we get to the next data point. Then here again, once we start at this data point, then we need to go 1, 2, 3, 4, 5, 6 for the next data point. Also, stride, and right next to this, I'm going to explain offset as well, is not specified in number of values, like I'm saying here, 6, but instead it is specified in number of bytes. So of course, because we are using floats, this needs to be multiplied by 4, which will give us 24 for a data set like this. So keep that in mind. Sorry for this, I was a little bit sloppy with my explanation here. On with the rest of the video. Now in our case, we have a tightly packed array where after every 3 values for every vertex, we don't want to skip anything because the next data is already right next to us. So in that case, we want to specify stride to be 0. Now the last one is the offset, and we also want that to be 0. And the offset is basically just how much junk is in front of your array before that you want to start reading. So in this example here, we have garbage, 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 and then we have our first actual data that we want to use. So in this example, we'd have to specify 4 here. Then it will skip the first 4 values, and it will start reading here. Then of course it will skip the next 3 if we set stride to 3, read 3, skip 3, read 3. Right, but again, our data that we specified up here is perfectly tightly packed, so this can all be 0. Now I will show you later on in this video why stride and offset may be useful to us. Now the next step is to just draw what we have. So draw arrays. This will require us to specify the primitive type, or basically just whatever we want to draw here. So we want to draw triangles with our data. Next, we need to specify the first vertex that we want to draw. And of course, that will just be index 0, the first 3. So it's just index 0. And then the number of vertices that we want to draw. So that is 3. So we have 1, 2, 3 vertices in here. Right, of course, we can also have 2 triangles in here, like this. And then we would have to specify 6 in here to draw all of these 6 vertices. And that will just draw through 2 triangles for us. Okay, let's get rid of what we added here. I think this should be okay. 1, 2, 3, 1, 2, 3, 1, 2, 3. Yeah, that works. And then of course, the last step is to unbind everything. I'll just copy paste this. This code isn't particularly interesting. Just unbind the buffer. Of course, we have to specify that we are talking to the array buffer. Then unbind the VAO, then we can delete the VAO, and then we can delete the buffer. Nice, then this should work. Let's check it out. This should give us our triangle back. Perfect. Now, of course, if we wanted to, we could specify here that we would want to get the GL BufferStorage, because of course we are not writing to our buffer at all after we create it. So we can just copy paste all of this, because it basically requires exactly the same parameters except for the last one. Because of course static, dynamic, and stream really don't mean anything when you cannot update your buffer data anyway. So we have a bunch of other flags here. Now again, I am not going to explain every single flag here because buffer storage is not the primary focus of this video. So we're just going to put in none here. I will probably explain what these other values mean in the advanced video. All right, so here we go. Let's check this out if this works. There we go. That works perfectly fine. Now, because you cannot update this data, it might be so that this is slightly faster than using GL BufferData. But again, it might be that it is not faster than BufferData. It might even be slower. That is totally dependent on the driver that you are running. I am planning on actually testing this on my driver in a sort of GL myth-busting video at a later point in time. For now, I would suggest just using BufferData, or if you really want that last drop of speed, which I can very much understand, then just measure how much time they both take and then just decide for yourself which one is faster and which one you should use. Now what I want to do is I actually want to add another buffer. I want to add more data. I want to add color data. Now let's say I want to add 3 colors per vertex, right? I want to add an RGB value for every vertex of our triangle. And then I can dynamically change the color of the triangle that we are showing. So let's say I want one triangle or one corner to be red, right? So that is 1 for R, 0 for G, 0 for B. Then I want the other one to be blue. So that will be like this. And then the last one, of course, to be green. There we go. Now we have an array with color data. Now, of course, for that, we would have to generate a new buffer, colors, right? That is perfectly fine. And then after setting the data for the vertices buffer and binding that vertices buffer to the VAO, I want to do exactly the same thing for my color buffer. So here I want to bind buffer colors. And again, I want to bind that to the array buffer. Notice that this will overwrite the vertices that was already bound here. So we will no longer be writing to the vertices buffer. Will now be the colors buffer. Okay, this will then remain the same, of course. Then the length will be colors.length. I call this color. That's a little bit confusing, isn't it? All right, anyway. Color.length. And then color as the data that I input here. Then, of course, the buffer usage is exactly the same. Static copy should be completely fine. We are never overwriting this data anyway. Then I want to enable index 1 in our shaders. And also in here, I want to write the index 1 in our shaders. And of course, I want to have an R, G, and B value per vertex. So that is 3 values per vertex. They are float values. I do not want to normalize them. I don't want to normalize this either, even though it really doesn't change anything. And then, of course, 0 stride and 0 offset, because this is a tightly packed array. Now, of course, I am going to have to delete it as well. So let's also delete the colors buffer. And then as a last step, we are going to have to add all of these colors into our shaders. So let's do that real quick. Here we go, our fragment shader. And I basically want to just read all of this data into our fragment shader directly. Because of course I don't need the colors in the vertex shader. Then I can specify here location equals 1. That is very important. then I can say here this will be vColors. And of course it will be a vec3. Save, yes. Of course it will be a vec3 for RGB. And then here in the output color, we can say, well, this is just vColors dot R, vColors dot G, vColors colors dot B. And RGB should be the same as X, Y, Z or A, B, C, I believe. And then the alpha value will just be 1. I don't need to specify the alpha value. All right, let's check this out. So now we should have a crash. Oh, would you look at that? Ah, yes, I realized my mistake here. So we are using a slightly older version of the GLSL. And for that, I am required to input all of my buffer data into my vertex shader, then output it towards the fragment shader. I cannot directly read it into my fragment shader. Right, so in vec3, and then I want to say color in. And then here, of course, I want to say out vec3, I'll call it color in. Of course, these have to be the same. So I will just say that color in, and that will just be vColors. Oh, that is way too much indentation. Save that, save that. Let's try that again. Oh, of course, I'm still using vColors in my fragment shader. Whoops. Let's change that, right? Without the semicolon in there, please. Yes. Okay, so it's a good thing that we have all of this debugging code, and there we go. So we have a red corner here, a blue corner here, and a green corner there. Then, of course, the fragment shader makes sure that everything is nice and smoothly blended over the surface of the triangle. There we go. We have our colors. Now, there is another technique to get this done, right? And that is something that I still want to show you. So let's just say that we don't really want to make 2 arrays and 2 buffers, because that is just 1 buffer too many, maybe. It's a bit annoying. So let's just say that I'll call this VertexData. I'm just going to say that this is, well, first it's going to be the position of the vertex, and then it's just going to be the color, right? And then next, I want the other position, this one, and then I want the other color. There we go. And then for the last one, and I think you can see where this is going, right? So now we have the vertex and color data intertwined into one array, where the first tree is vertex, next tree is color, then vertex, color, and so on and so forth. So what we can now do is I can get rid of my second buffer, because I'm not going to need that one anymore. And then the first buffer, I can just change like so. So of course, I changed the name, I changed it to VertexData. But of course, everything is still float, so I can just say VertexData.length times size of float, and that will just give us the size of this array in bytes. That works the same. I can just throw in this entire array here. That also works exactly the same. So now if we run it, oh, of course, I also have to delete colors to delete the delete color buffer here. Now if we run it, yeah, we're going to get something that's a little bit weird. That is not the triangle that we used to get, right? That's a bit weird. Like this position is way off and it's black. That's not quite right. Now, how we can fix this is with this one, with the stride and the offset. And actually, going to have to copy this bit as well. So what we can do here is for index 0, which is just the vertex positions, we can say, well, the offset is 0, right? Because the first vertex position is right at the beginning. But then I need to skip 3 data points before I get to the next vertex. stride is specified in bytes, so we'll have to go to 12. And stride is actually going from the beginning of our first entry to our next entry. So it's actually 24, because we'll need to go 1, 2, 3, 4, 5, 6 before we get to the value that we want to get to the next value. And of course, 6 times 4 is 24. And if we specify that, then of course we do get our nice triangle, but it is still black. There we go. So what we can then do is we can enable VertexAttribArray 1, which is of course for our colors. And then we can specify that our stride in fact is also 24, of course, but our offset in bytes is 1, 2, 3 times 4 is 12. And then we should see our triangle. There we go. So now we have specified the vertices and the colors of our triangle in one array and in one buffer. So that is also a completely valid way of doing it. It is basically just whatever you prefer, right? In one case, you'd have to interleave your data into one array, which might be a bit annoying. But in the other way, you'd have to keep track of 2 different arrays and 2 different buffers. So that might also be a bit annoying. It's just whatever you prefer, basically. I don't think there should be much of a performance penalty on either. But again, that might be something that I could check in a myth-busting video. Anyways, that was it for today. Keep an eye out for the advanced buffers and VAOs videos, where I will go into more detail on dynamically updating buffer data, reading buffer data, also writing to it in the shaders, and of course, the more advanced buffer targets and the more advanced buffer usage hints here. All right, hope you all enjoyed this video. If you did, then please leave a like and maybe even consider subscribing. And then I hope you all have a wonderful day. Bye bye.